Hello. So I've been doing a little bit of work on graphite recently, and something I noticed about the crystallography of graphite that I think is worth sharing with everyone. Um, I'll start by saying what graphite consists of. Well, graphite consists of layers of carbon atoms arranged with sp2 bonding, sp2 hybridization. And what that means is that for every carbon atom, if we take a carbon atom, there are three other carbon atoms surrounding it, which correspond with the directions of the sp2 orbitals. Now, what graphite is consists of layers of these graphene layers stacked one on top of the other, but they're not stacked comfortably. They're stacked in a kind of an odd way, in that the carbon atoms are on the next layer are stacked one on top, or half of them are stacked directly above the carbon atoms in the first layer, and the rest are positioned over the holes made by the hexagonal rings of the graphene layer. So if I can do that on a flat surface, what I can show you, I can do it here. What we have is, there's my graphene layer, and how many people, or most people, envisage the crystal structure is that the next graphene layer sits sits like this, like in a really very unstable position, where there are one set of or half of the carbon atoms are sat directly above the next the first layer of carbon atoms. So one of the things I noticed is that some people would call this hexagonal-close-packed, and I'm thinking, oh, how is that close-packed, and how is it, well, hexagonal for sure. There was some hexagonal symmetry, but it didn't, the positions of the atoms didn't match what the symmetry elements that make up the hexagonal-close-packed, which is P63/MMC, which you'd have to go and look up what these symmetry elements are, but for a hexagonal-close-packed it makes sense, P63/MMC, but for graphite I couldn't figure out where the symmetry elements lay to have that kind of symmetry. Maybe just call it loosely hexagonal, which is fine, which is what many people do, and some people describe it as a rhombohedral structure. Now, I'm not sure that it's exactly then the same stacking, it's slightly somewhat different. But what I wanted to point out is one of the things in doing my research, I come across some work by a guy called Linus Pauling. Now, Linus Pauling is a very famous chemist, and he obviously did a lot of work on crystallography because he did some work on graphite. Nobel Prize winner, by the way. He did some work on graphite, and he concluded that graphite was actually an orthorhombic crystal structure. So what Pauling deduced from the diffraction patterns, and remember they're just patterns that powder diffraction patterns that people used in those days, in the 50s, to where they basically looking at where the high intensity spots are, reflections are in the X-ray diffraction pattern, and he deduced that the overall symmetry could only be reconciled with a structure which was more like that, and this is an orthorhombic structure. So Pauling suggested that it was an orthorhombic crystal lattice, and I kind of like that because that's much easier to envisage than this thing, which is kind of delicately balanced. And it's much easier to think of a more close-packed structure, which is that. It basically falls into place. We have our orthorhombic structure, which is what Pauling envisaged. What's interesting is that you still have hexagonal symmetry, because the ratio of the A and the B parameters in Pauling's structure are basically the exact ratio for A and B orthorhombic unit cell in a hexagonal close-packed material. So you can, for any hexagonal close-packed structure, you can also apply an orthorhombic unit cell. Doesn't necessarily, but it doesn't follow that for any orthorhombic structure you can create a hexagonal close-packed unit cell. But when you create an orthorhombic unit cell from the hexagonal unit cell, the ratio of the A and B parameters are of a very specific ratio, which is 1.732, which is basically root 3. So Pauling said, I think it's an orthorhombic structure. There's 2 layers, and there's the next 2 layers of Pauling's orthorhombic structure. It's nice and stable, more close packing, and according to Pauling, was more consistent with all of the reflections he saw in his diffraction patterns. The beauty of what Pauling is proposed originally really has to do with other observations that people make. Many people, or I've seen other references to both hexagonal close-packed, hexagonal, rhombohedral, but also to stacking faults and the existence of dual phases, one with AB stacking and one with ABC stacking. So the existence of the dual phases was intriguing because, according to Gibbs' rule, there should only be one phase in equilibrium, so it can't be an equilibrium structure. But you can get a dual phase structure by a martensitic transformation. So if this is let's assume that this is graphite. And just like any hexagonal close-packed material, you can shear it in the basal plane. The thing is, you can't shear it in the same direction on each successive plane, and that's why you can't get twinning on basal planes in hexagonals. But what you can do is you can shear every other plane. So if we take my first plane here and then look at the second plane, I'm going to shear my second plane. I can't shear the third plane, which is the next A plane, in the same direction, but I can shear the next plane in the same direction, which is the next B plane. So what we have now is basically an ABC stacking sequence, not the AB stacking that existed before, and that is then consistent with observations of ABC stacking that are coexisting with ABA stacking in graphite. So you can have 2 phases existing if one of them is a shear of the other. It's a martensitic shear. But you can't based on Gibbs' rule and thermal equilibrium. So there it is. That's my sheared phase, and go back to my original Pauling's orthorhombic phase. Sorry for the fingers getting in the way. As I probably repeating myself, there is some degree of hexagonal symmetry in that. So if you look at a powder diffraction pattern, you'll probably notice peaks that, oh, that's consistent with hexagonal. But is it really truly hexagonal? Well, it's, according to Pauling, it's really truly orthorhombic, but with a ratio of the A and B planes, sorry, lattice parameters, which are also consistent with hexagonal symmetry. So it's kind of complicated, and I haven't thought about it a lot. I just wanted to share this with you, and I kind of like Pauling's idea. It's a nice, stable structure, but it's still held together where the layers are held together with van der Waals forces, so it's still relatively easy to shear one with respect to the other. The shear I just described was always in one direction, one partial in one direction, but then you can shear in any number of kind of different directions, one layer with respect to the other. And as these layers are bound together with van der Waals forces, that shearing is very easy. Graphene layer itself is very strong because it's covalently bonded. And that's all I have to say about that.